Okay, so the product of functions is when we get two graphs and we physically times the two graphs together. So there are two ways that we can calculate the product of functions. The first way is the algebraic method, which will only work for easy functions like in this first example. So if we times these two functions together, x minus 2 and x squared plus 2x plus 4, we're going to get x cubed plus 2x squared plus 4x minus 2x squared minus 4x minus 8, which is x cubed, they die, minus 8. So this is a cubic function with our y-intercept equal to minus 8, and our x-intercept is going to equal 2. So if we plot minus 8 and 2 over here, our cubic function is going to look something like that. It's a weird scale. So that's how we calculate the product of functions. That's using the algebraic method. But again, if we have two very difficult graphs, then we need to do the graphical method, which I said again is the better method to calculate the product of these two functions. Now, when we're calculating the product of two functions, it is useful for us to consider what our final answer would be if we did the algebraic method. So for example, if I times my two functions together, it's useful to consider, even though we're doing the graphical method, it's useful to consider what would be the leading term of my product. In this case, the leading term would be x cubed. Now, we should know, or we're going to learn, that any odd power of x, so x cubed, x to the power of 5, and x to the power of 7, will always start in the first quadrant and end in the third quadrant. If it's minus x to the power of 3 minus x to the power of 5, for example, it's always just going to be the opposite, start in the second quadrant and in the fourth quadrant. If we have even powers of x, so x squared, x to the power of 4, x to the power of 6, x to the power of 8, it's what we call an even function. And what that means is all of our even powers of x, the functions are always going to start in the first quadrant and end in the second quadrant. And for our negative even powers of x, so minus x squared minus x to the power of 4 minus x to the power of 6, it's going to start in the fourth quadrant and end in the third quadrant. So it's useful, even though we're doing the graphical method, to consider what is my graph generally, where does it have to start and when does it have to end. I know in this question that it's a cubic function, so I know it has to start up here and end down here. I do those little scribbles just to give me an idea. Now we're going to physically calculate the product of these two functions. So I like to, just like we did with the sum of functions, to start on my y-axis. So here we've got 1, 2, 3, 4, and down here we've got minus 2. So 4 times minus 2 is minus 8, so we're down here. After I've looked at the y-axis, I like to then look at the x-axis. So here we've got 0, and up here we say we've got 12. 0 times by whatever our parabola is still going to be 0. So we're over here. That's one of the interesting properties, and a property we need to remember for the product of functions, is that whenever we see our x-intercepts, then our product will always have the same x-intercepts, because 0 times by a number is still 0. Up in the first quadrant, up here, we've got a positive times by a positive, so our graph is just going to go up like that. In the middle, between x equals 0 and x equals 2, we've got here, say, positive 7 times by minus 1, so we're going to have approximately minus 7, so it's going to be down here. So we know it's going to look like that. Now, when we take the product of functions, it's different from when we add. So if I take the product of a negative function, which is down here, and the positive function, which is up here, a negative times by a positive is a negative. So our graph is going to exist down in the third quadrant like we expected. If we just consider a few points, here we've got the point -3, and up here we've got the point +3. So we're going to be down at -9. So our graph is going to go down like that. So that's my answer there. Now, of course, in an exam, you would then need to go, okay, well, I know this is a cubic function. I know that's there. So it looks roughly like that. All right. I'll just pause there. Okay, so again, we're taking the product of these two functions. When we take the product, yes, we can do it algebraically, but it's good practice doing it graphically. We know that if we took the product of these two functions, then it's going to be a parabola, because it's going to have a leading term of 3x times x, so it's going to have a leading term of 3x squared. Now that's a positive parabola, so it's going to start up here and end over here. Right. So let's draw those two graphs, 3x plus 2, and I think in class we actually abandoned that graph because it was just, the scale was weird, so we're just going to do it over here. 3x plus 2, well, I've got a 2 up here, and then a -2/3, so it's going to look like that. And then x minus 1, we've got 1 and 1, so it's going to look like that. That's awful, I need to make that a bit straighter. Oh my god. Okay, that's the... Oh my god, I apologize. This is awful. Okay, that's the best it's getting. So, let's consider what happens when we take the product of these two functions. So here we've got 2, and down here we've got -1. So 2 times by -1, I might make a new colour. 2 times -1, we're going to be down here at -2. Again, at our x-intercepts, we're going to have 0 times by something, so we're going to have a function that's here. Again, we're going to have another 0 here. Over here, that's going to be -2/3. Now, this is another one of the important properties of the product of two functions. So, down here, that's where our function is negative for both of the functions. So 2 negatives is going to make a positive, which means the product is going to actually be up here. So our graph is going to be up here when we're over behind -2/3. So when we're over here. In this part of the graph, we've got 2 positives. So 2 positives make another positive, so we're going to be up here. So our graph's going to look something like this. And then again, we might want to draw that. So we've got -2/3 and 1. So it's going to look like that. All right. Again, I think we abandoned that graph in class because it wasn't very good. So let's graph g of x is equal to x squared minus 2x minus 8. So that's going to be x minus 4, x minus 2. So our x-intercepts are going to be 4 and... No, so x minus 4, x plus 2. So 4 and -2. So 1, 2, 3, 4, -1, -2, -3, -4. I might go 2, 4, 6, 8. 2, 4, 6, 8. Okay, let's graph our parabola first. So we've got -2 here and 4 over here. We have an intercept of -8, so my parabola is going to look like this. And then I've got my cubic function, which is -x cubed, which looks like that. What happened there? -x cubed, which looks like that. Right, so again, we're just going to physically calculate the product of these two functions. So if we look upon the y-axis, 0 times by -8 is still 0, so we're going to have a point here at the origin. Over here at 4, we're going to have another x-intercept. And over here at -2, we're going to have another x-intercept. Let's think about where our graph's going to be on either side of each of our x-intercepts. If we look at the right-hand side of our 4, we've got a positive times by a negative, so our graph's going to be down here. Between the origin and 4, we've got two negatives, which make a positive, so my graph is going to be up here. Between 0 and -2, I've got a positive and a negative, so my graph is going to be down here. And between, when we're on the left-hand side of -2, we've got two positives, so my graph is going to be up here. Sometimes I like to do that type of shading. It helps us with our graphs, and it helps us understand, to get a general idea of where our graph's going to be. We also know that if I find the leading term of the product, it's going to be -x to the power of 5, which is an odd function, so we know it has to start at the top and end at the bottom. And it's a negative function, so it means the function has to start up here and end down here. So let's consider what's going to happen. We might consider a few points. So over here, we're going to be down here. So it's going to look a bit like... here we've got like -1 and 1. So 1 times by -4, we've got about -4 down here. So it's going to be about down there. If we look over here, we've got about -4.5 times 4.5, which is, -4.5 times by 4.5 is 20.25. So my graph is going to be up here. So again, if we look where our two graphs intercept here, it's about at y equals -4.5. If we times those two numbers together, we get about 20 point something. And then we know our graph has to be down here as well. So if I just connect those dots, I'm going to have something like this. I might rub out some of the highlighter. Again, with these functions, it's not so much important to have exact values. What's more important is that we get the general shape and understand what's happening in general. So that's a bit messy. These questions are messy, but if we will go over to our final graph, we know we've got something happening at 4. If I might change this to a 4. We've got something happening at -2. So let's make this a 4. So -2 would be here. And we've got something happening at 0. So it looks a bit like this. So our graph looks something like that. I'll just move that away. So our graph looks a bit like that. Okay, I hope that makes sense. Let's also talk about quickly the quotient of functions. So I think I wrote that down somewhere. Nope. Okay, so the quotient of functions. So when we talked about the subtraction of functions, I know this technically is not in the syllabus, but when we talked about the subtraction of functions, we instead looked at it as the addition of the negative. So same idea with the quotient. If we had f of x is equal to h of x over g of x, well, instead of graphing the division, all we need to do is graph h of x and graph the reciprocal of g of x and multiply them. So the quotient of functions, we need to graph the reciprocal of g of x, and then we multiply them like we would in the past examples that we just did. All right, I hope that makes sense.